This is our last section in acids and bases. It's on neutralization. So a neutralization reaction, definition, a reaction in which an acid and a base in aqueous solution react to produce a salt and water. So we're going to have an acid plus some kind of a base, giving us salt plus water. A salt, it's an ionic compound made up of a cation from a base and an anion from an acid, is all it is. So something like sodium chloride, it's a salt. This is from sodium hydroxide. This is from hydrochloric acid. This would be an example of a salt. Okay. Types of reactions. Now, this is something that we'll come back to when we talk about types of reactions, but this is a double replacement reaction. And we'll see why that is when we talk about types of reactions with the next unit. So here's an example of a neutralization reaction. We have NaOH as a base and hydrochloric acid as an acid. They're reacting, giving us a salt and water. So what's really going on here? Well, since these species are all strong, okay, the reactants, so we have a strong base and a strong acid, everything comes apart 100%, which means things don't exist as complete NaOH units. They exist as sodium units and hydroxide units, and this doesn't exist as HCl. It exists as H plus and Cl minus, right? That's how it's existing. Well, the two in the middle here, those two are going to react to form water. H plus and OH minus give us H2O, right? Those are the two pieces that make up water. Down here is a picture of it. They're using H3O plus, again, same thing as water, as H plus, but reacting with the hydroxide ions, giving you two waters there instead of just one if we're using H. The salt is whatever's left over, the other two things, right? So in this example, right, we have Na and Cl are the leftover things. Well, plus 1 and minus 1 react to form a 1-to-1 ratio salt, NaCl. It's still aqueous, it's still dissolved in water, but that is a salt. Okay, so we're going to start seeing titrations. This is using stoichiometry to determine how much of a particular reactant is needed to neutralize the other reactant. The definition of a titration, it's a method for determining the concentration of a solution by reacting a known volume of that solution with a solution of known concentration. I know that sounds kind of complicated here, but on the next slide we're going to draw out what happens, and hopefully that should clear it up. But basically what these problems are going to be is stoichiometry with acids and bases. Okay, so this is what a titration looks like. One of the labs we're going to do, okay, is a titration lab. Essentially what you have is this setup here. You've got this really tall, narrow piece of glass that's got a lot of graduations along the side. So it's telling you it's a very accurate piece of technology, okay? It's very expensive. These are called burettes. And so you suspend that from a ring stand and a clamp, okay? And what we're going to do is we will fill this, right, we'll fill this up with a quantity of base. So what we put into the burette, we have a base with a known concentration, and we can also know the volume because, well, there's markings along the side of the burette. Okay, so I guess I should probably draw it like that. That's okay. All right. So we know the volume because there are markings or graduations along the sides of the burette. So we have the known concentration. We also have a known volume. All right. Underneath it, in a beaker, we will have an acid. Typically, usually put the base in the burette and the acid is what we are testing. An acid of known volume. Okay, so you measure out a volume ahead of time, then you pour it into the beaker. But an unknown concentration. Okay, so we know its volume, we don't know its molarity. Okay, so we're testing this. And essentially what's going to happen is we are going to let this base drip into the acid, and that is going to begin to neutralize it. It's going to become less and less acidic as it reacts with more base. Okay, its pH is going to rise depending on how concentrated it is here. It's going to tell you how low it starts, but the pH is going to rise as I keep adding base. As I keep adding base into the beaker down here. And what I typically do, and by the way, the piece that you connect with right here, that you open this up with, this is called a stopcock. Okay, that's actually what it's called. And you open that up to allow the base to drip down into the acid. Now, typically, we will add a chemical to the beaker down here. So into the beaker, and that is going to be something that's going to change color depending on whether something is acidic or basic. This is called an indicator. Okay, so it changes color based on pH. So what we're looking for, this is done, at least if we want to neutralize it, when the pH is 7, since that's right in between an acid and a base. So we want an indicator that changes color at a pH of 7, if we can find one. Unfortunately, there are some. So we'll add an indicator in there. The most common one is one called phenolphthalein. It's kind of a mouthful. Phenolphthalein, which is, and you'll want to put this down because we're going to see this next week. Phenolphthalein. It is clear in acidic solution, and it is pink in basic solution. So if we add the chemical in here before we start, all right, even if, so let's add that one there, okay, and so if we put a couple of drops of that chemical into the beaker at the beginning, it will still be clear because it's starting acidic, okay. This reaction is done, the titration is complete when the solution down here is neutralized at a pH of 7, and we'll know it's done because it turns pink. So all of a sudden, this entire solution will turn bright pink when it's complete. So that's our setup for what a titration looks like. So now we'll go to the math behind it. Okay, so how to calculate an equivalence point, that point at which, for our purposes, the pH was 7, when I had equal amounts of acid and base. So here's a reaction between hydrobromic acid and lithium hydroxide, giving us the salts lithium bromide and water. It says if 25 milliliters of a 0.350 molar HBr solution is titrated with 0.100 molar LiOH, how many milliliters of LiOH are needed to reach the equivalence point? So I'll show you the stoichiometry way of doing this, and then I'll show you kind of the shortcut way of doing this. We want to know how much volume in LiOH do we need. Well, we would first need to know the number of moles of acid. So we would take the 0.0250 liters that they give us of HBr and multiply that times the 0.350 molar concentration given here. And that's going to give us times 0.35, 0.00875 moles of HBr. Then I want to figure out how many moles of LiOH is that equivalent to. So then it would be multiplying times a mole ratio. So we got, 0.00875 moles of HBr times, okay, mole ratio here would be looking for LiOH on the top and HBr on the bottom. It's a 1/1 ratio. So my number of moles of base is 0.00875 moles of LiOH. And then it gives us the concentration here. It wants to know the volume. And if you remember, molarity is moles over liters or moles over volume. And we're given molarity, and we just found the number of moles of base. So solving for L, like the liters would be moles divided by molarity, rearranging my variables. And that would be 0.00875 moles divided by the molarity given of 0.100. Okay, so that's just going to move the decimal place basically one spot over. This would be 0.0875 liters. Or if you want to think of it right in terms of milliliters, since my initial value was in milliliters, that would be 87.5 milliliters. Either one of those answers would be acceptable. Now, it's a little bit of work, and it should make sense. The acid is significantly more concentrated than the base, and I have 25 milliliters of this. So to neutralize it, I'm going to need volume-wise a lot more base than acid, so 87.5. There's a shortcut. So you don't have to do all of this, but it only applies if everything in the balanced equation has a coefficient of 1. The good news is that happens a lot of times. But if everything in the balanced equation has a coefficient of 1, okay, here's the shortcut. It's really simple. The equation is this. MAVA equals MBVB. All the coefficients have to be 1. But the good news is pretty simple. So the only thing that we don't know here, because it wants to know what is the volume of base, how many milliliters of LaOH, volume base. So I'm solving for VB. VB would be MAVA over MB. Okay, and mathematically, based on that, the molarity of the acid was 0.350 molar. The molarity of the, oops, put that in parentheses there. The volume of the acid was, and we can actually leave it in milliliters here, 25.0 milliliters, divided by 0.100 molar. My answer would come out in milliliters, 0.35 times 25 divided by 0.1. Gives you 87.5 milliliters. Okay, so just again, this only works for all coefficients of 1. Okay, so you can't do this. If any of these numbers up here were 2, we couldn't do this. But MAVA equals MBVB, important equation to make sure you got in your notes. Okay. Frequently, that's the version of this. If you get one that's not 1 across the board, we'll show you what that looks like. Basically, you just have to do the stoichiometry to it. Okay, so here's one that has not all 1s as coefficients. So we actually have to do the stoichiometry to it to make sure that we're doing this correctly. 15 milliliters of 0.25 molar HCl titrated with CaOH. Takes 45 milliliters to do that. What's the molarity of CaOH2? So we can't use MAVA equals MBVB because my coefficients are not all 1. So I can't use that here. We'll start with the 0.0150 liters of acid times its molarity, 0.250 molar. And that is, let's see, 0.015 times 0.25, 0.00375 moles of HCl. And then I want to turn that into CaOH2, so 0.00375 moles of HCl times, right, mole ratio. So it's basically just stoichiometry. I'm doing it in separate steps here just to be very clear about it. So here's my setup. This is a 2, this is a 1. So really that's going to be divided by 2, and that's going to be 0.00188 moles of CaOH2. Okay, and then when we're trying to find the molarity of it, because it says it takes 45 milliliters, right? Molarity is moles over liters. So we got 0.00188 moles divided by 0.0450 liters. It's going to give us 0.0417 molar is the answer there. So It is stoichiometry. It's not nothing too difficult. But we just have to remember calculating things in molarity. Here we can't use MAVA equals MBVB because not all the coefficients are 1. All right, one more here. This is really an example of an excess reactant type of problem. Okay, is the way to think of this. Really, everything we've done so far assumes that the final pH is equal to 7. Okay, everything so far assumes neutralization. We don't go past that point. We only go to 7. So the question is, what happens if I add too much or not enough? What's the pH? And you might remember, right, that pH is negative log of the hydrogen or hydronium ion concentration. pH is also equal to 14 minus POH if we need to do that. So that's all coming from the pH squared, right? So that's where that was coming from. Okay, so this question says if 52.3 milliliters of 0.500 molar HCl is titrated with 21.7 milliliters of 0.400 molar NaOH, what is the pH of the solution? How much more NaOH must be added to reach the equivalence point? Well, we know off the bat, based on this question here, the second part of this, how much more NaOH must be added. That means that NaOH is the limiting reactant in this situation, and HCl is the excess reactant. Okay, we can actually solve this question first. Everything is a 1-to-1 ratio, so we can solve that question first with MAVA equals MBVB, and then we'll figure out what the pH of the solution is. All right, so we're going to solve this question first, and then this question second. So to do the first one, MAVA equals MBVB. We're trying to find out how much base did we actually need to add, because this apparently was not enough. So the molarity of the acid here is 0.500 molar. The volume of the acid was 52.3 milliliters. The molarity of the base, by the way, I'm rearranging this to solve for VB if you haven't figured out what I'm doing. The molarity of the base is 0.400 molar, and so that's going to equal VB, which is equal to, let's see here, 0.5 times 52.3 divided by 0.4. That is 65.4 milliliters. Okay, so far, this would be at neutralization, right? This is at the neutralization point, okay, equivalence point. But we're not there yet, because how much did we suggest we've only added? We've only added 21.7, so how much more needs to be added? Well, it's just 65.4 milliliters minus how much we'd already put in, 21.7. So 65.4 minus 21.7 is 43.7 milliliters more. So that's how much still needs to be added. Needs to be added. Okay. And so the next question is, before we add that 43.7 milliliters, if we stopped before that, after only 21.7, what would the pH be? So I'm going to shift everything up here so I can have a little bit more room. So this will be question number 2. All right, what is the pH? Well, right now, okay, that means I have excess acid. And we're going to assume, okay, that I have quite a bit of excess acid. I need to figure out how much base I currently have and subtract that from moles of HCl. So, how we're going to solve this, since I have excess acid, I'm going to start with the base. That's my limiting reactant. So I've got 0.0217 liters of NaOH times 0.400 molar. And this is going to give me moles of NaOH that I've currently added. This is 0.00868 moles of NaOH. Okay, I could turn that into moles of HCl. But what I need to do is also find out how many moles of acid that I started with, actually. So this would be 0.0523 liters times 0.500 molar. Okay, 0.0523 times 0.5. And that is 0.0262 moles of HCl. And so essentially this, since everything's in a 1-to-1 ratio here, this volume of base is going to eat away that amount of acid. That's how much acid is going to get used, is this much. It's all in a 1-to-1 ratio here. Okay, if you really want to write this out, we can write out 0.00868 moles of NaOH times 1 mole of HCl for every 1 mole of NaOH. And that means that we use 0.00868 moles of HCl. So this is how much gets used up. This is how much we started with. Okay. I'm going to scroll down a little bit more again, give myself some more room. Well, take the starting minus the amount used, 0.0262 moles minus 0.00868 moles. And to the, let's see here, 10,000th place, this is 0.0175 moles of HCl. But it wants a pH, which means I also need to find its concentration. Since this is an acid, this is a long problem, I agree. H plus, right, I'm finding the concentration here, 0.0175 moles of HCl, or H here. Divided by, well, my volume, it's 2 volumes. It's this volume of base and this volume of acid that have been added together. So 0.0217 plus 0.0523. So that is 0.0740 liters. So we got 0.0175 divided by 0.074. My hydrogen ion concentration is 0.236 molar. And going all the way back to what my equation for pH is, it is negative log of the hydrogen ion concentration, which here we said is 0.236. Okay, so let's see here. That should give us a pH of 0.63. So it's still pretty acidic even after all of that. Okay. Problem number 2 is a long problem. This is very likely to end up as more like an extra credit type problem on a test because there's lots of reasoning to get to your answer there. Okay, acid-base indicators. I briefly mentioned this when we were drawing up the titration. So how do you know when your neutralization is complete? pH meters, yeah, they exist, but they're notoriously unreliable and hard to predict. Chemical dyes can be used instead. So chemical dyes whose colors are affected by the pH of a solution are called indicators. When a pH reaches a certain value, the indicators change color. This is the end point of the titration. So using the example that we were talking about before, phenolphthalein, okay, it is colorless when the pH is less than 7, and it is pink, okay, when the pH is greater than 7. So the moment that it turns pink, it's crossed the border over into being basic. Different indicators change color at different pHs. They're not all the same. Phenolphthalein, bromothymol blue, there's a whole bunch of these things. This is the one that you need to know the name of, phenolphthalein. We're going to see that a lot.